when you add a buffer to it, when you add a common drain stage to it, then it becomes an operational amplifier, because in that case you are getting ideal or closer to ideal characteristics of an op-amp that you have studied. Almost very high, almost infinite input impedance, ideally very large gain, at the same time very small output impedance. This is a characteristics of an ideal op-amp. So far still this is not op-amp, this is an operational transconductance amplifier. Only thing that is missing is a common drain or an appropriate output stage which is going to offer low impedance. So we will have dedicated discussion on output stages. So what kind of output stage we can have, and how to bias those output stages, how to design those output stages. Those we will have dedicated discussion. But let us go through some examples on the OTA first. So in this particular circuit, going forward, uh, our main goal is to basically get a overall large gain. First stage, what is the role of the first stage? First stage, we see that the gain is not very significant, right? It is just giving you, it is like a common source amplifier with diode connected load. And the gain of this stage is just GM1 by GM2, right? That's what we have discussed in your common source case. If it is a transistor number M1 and M2, the overall gain on this stage is just GM1 upon GM2, which may not be very significant. So why? What is the use? What is the benefit of this first differential stage? Why are we not using? So all the gain we are seeing, the GM RO square gain is coming from the second stage. Uh, but the first stage, what is the purpose?
So
Why? No.
the
Yes.
current signal from a voltage signal, and then we can use that to in the current mirrors. So just that voltage to current conversion, I think we are using this first stage.
Uh, Okay, so you are saying that it's a voltage to current conversion. So the V to I conversion, because this is a transconductance amplifier, so we are able to do the V to I conversion using this stage. So as we discussed yesterday, we are having small signal currents produced at the two outputs of the first stage, depending upon the input signals applied, and that basically reflects in the output stage. And that scheme we had discussed how it is reflecting. So the small signal current in the M4 is directly mirrored into M6, and small signal current in M2 gets mirrored into M5, and then it goes to M7, then it goes to M8, same mirroring, right? So M3 to M2 mirroring, sorry, M3 to M5 mirroring, this is 5, and then the same current goes to M7, M7 to M8 mirroring, and therefore it comes out of M8, and then for M4 to M6 mirroring. So these are the two mirroring, multiple stages of current mirroring happening. This concept we had discussed in the beginning in the current steering circuits. So that's why we discussed that part, because ultimately in this amplifier you are seeing current steering happening. Okay, that is a good answer. We are having a V to I conversion in the first stage. What else? That is not the primary reason though. So that is maybe an auxiliary reason. Primary benefit of the first stage is what? Is a differential stage, right? So differential stage, what benefit does it have?
So we don't have the common mode noise.
Common mode rejection, right? So common mode rejection will be good for the first stage. It will be able to reject any common mode noise, and then it transfer only the differential signal to the second stage. The second stage in this case, of course, the output stage is single-ended. We are taking the output in a single-ended manner. There could have been topologies which are fully differential also, like we can on both side actually, just like on this side we have made this cascade load. On the other side also, rather than routing the current to the same side, we could have the output taken from the other side also. We could have the same cascade on the other side also. Then it would have been fully differential. Right now, this is not a fully differential amplifier. When we say fully differential amplifier, means input is also differential, output is also differential. This is the case where your input is differential, but output is single-ended. So the op-amp that you have, generally encountered in your introduction to electronics, etc., they are like this only. So you have plus minus and the single output. So it is a generally you have used differential input, single-ended output. This only you connect in different feedback topologies, and you get certain functions of amplifier, inverting, non-inverting, etc., etc. So all throughout you have been dealing with this kind of operational amplifier, differential input, single-ended output. But in uh, many cases, people prefer fully differential. That means you have the differential input as well as differential output. So this can be easily converted into fully differential also. You just have basically the other side, right? Whatever I have drawn, it will be replaced by the same cascode configuration. So that is the so even in case of single-ended output, the responsibility for rejection of common mode is on the first stage. That should be clear. Now, another so one of the advantage of this topology, if I ask you to find out what are the dominant poles in this circuit, how do we find out? So in this kind of circuit, if I want to do the frequency response analysis and try to understand what are the high frequency poles, so if I either I pan it or I delete this one, some of the things if I delete, rather than that I can just go down. I hope it saved the panned stuff also. Let me check. Yesterday I had panned and I don't see whether it has saved. I don't see anything saved. I don't know why. Let me check. I hope it will save. Yeah, so yeah, here it is saving. Fine, so it will save. Good. So yeah, so tell me, in this case, if I have to find out the frequency response, what is the strategy? So once again, I'm drawing that same circuit quickly. So what are the, how do we basically find out what are the high frequency poles? I'm not drawing all the biasing voltages. Ultimately, these voltages will be obtained from some current mirrors, right? So all those I'm not drawing right now. This is your bias voltages. So now if I say number this M2, M3, M4, 5, 6, whatever. So numbers may not be consistent from one picture to another picture, and one diagram to another diagram. That you don't worry about. So because it was difficult to maintain the same order. Okay. So now if I look at this, suppose I'm applying the V in plus over here, V in minus over here. Actually, this is the V in plus in this case. This is the V in minus because the polarity is, you have another stage in this case, which is reversing the polarity. So if you apply positive signal over here, the signal at the first stage goes down and output it will go up. So therefore, this is the positive terminal that I hope you are able to follow. This one will be the negative terminal for the OTA. Now here, if I want to see what is the high frequency characteristics, I just want to find out the poles, the critical poles. What are the critical poles in this circuit? Which nodes will give us critical poles? Yes. What is the most uh, dominant pole or the lowest frequency pole? Which node is going to give us the lowest frequency pole, dominant pole? That means the RC constant at that node is highest. Is, I hope this circuit is clear, right? Anybody is having any confusion in the circuit, I can explain once again.
So M9, right? Like
M9.
we're giving the input to M6 and then so this is the cascode stage.
Yeah, so which node of the circuit will give you highest frequency pole? Remember, in order to find out the pole at a particular point, we need to look at the overall small signal impedance from that node to the ground and also small signal capacitance from that node to the ground. So if you have multi-stage amplifier, we have discussed that at any node, if you want to find out, so we look into R equivalent and C equivalent. At every stage, we find out that C equivalent and R equivalent. What is the R equivalent and C equivalent from that node to the ground? And then we can simply, keep A1 upon 1 plus S upon P1, A2 upon 1 plus S upon P2, where P1, P2 are given by R equivalent 1, C equivalent 1, R equivalent 2, C equivalent 2, 1 upon that. So that we have discussed earlier. So that is the approximate analysis that we do all the time. So here in that approximate analysis, I need to find out what are the critical poles where I'm going to get a big RC time constant.
So between M11 and M10, we have a high impedance. So that
Yes. So here our impedance is highest, and in general, this may be also facing load. We may be having some CL which is driving the next stage. If it is a buffer stage, even in that case, it may be having significant parasitic capacitance. So because of the very high impedance at this node, this may be the dominant pole. Whereas all other nodes, if you look at the node here, here, these are low impedance nodes, right? So the impedance here is of the order of 1 upon gm. R up parallel R down, R up is 1 upon gm. Likewise, at this node, impedance R up parallel R down is again 1 upon gm. Likewise, uh, you know, if you look at, yeah, this nodes, you still have some impedance. It is of the order of RO, right? R up parallel R down, R up is RO. But in this case, the impedance here is much higher, gm RO times RO. So therefore, we get the dominant pole at the output. Others are all non-dominant poles. And looking at that, what is the benefit of having a dominant pole in the circuit? That we can try to understand. Let us see that. So when you look at, say, frequency response, we have discussed uh, ultimately when we are trying to use these operational amplifiers in feedback configuration, we need to make sure that after closing the loop, after doing the now in this case, suppose you want to operate this one as a unity gain amplifier. Unity gain amplifier means you have minus plus, you are applying some input voltage over here, V in, and output is connected to the negative input. So in that case, this output over here, V out, will be connected to the negative input over here, the gate of the M1. And in order to make sure that the overall loop is stable, we need to look at once again the phase margin and the gain margin using the board plot. So let us look at this quantity. How do we, in a multiple systems, how do we analyze the phase margin and the gain margin? So here, if you look at this kind of operational amplifier, uh, from this point to this point, if it is a positive input, you are applying the input at the positive terminal. This point to this point, there is no phase shift, 0 degree phase shift. And then you are applying it back to the negative terminal, which is basically having 180-degree phase shift with respect to the input, which is okay. Now, at higher frequency, if we start getting additional phase shifts in the circuit, because of which this becomes closer to 180-degree, then the overall phase shift from the input point back to the negative feedback will become 360-degree. So we have seen that overall, because of the poles, the phase also shifts. So at low frequency, if we ignore the effects of parasitic capacitances, the phase shift from here to here is 0. But as the frequency increases, poles are coming, you may get 180-degree phase shift at certain frequency. And then if the gain at that frequency is still greater than unity, you may get oscillation. So that kind of condition you have studied, Berghausen stability criteria in your oscillator circuits or even in your control systems or signals in systems. So this basic stability criteria should be known that overall at the point at which your frequency overall phase shift is becoming 360-degree, the loop gain should be less than 1. So looking at that, if you have a system like this where you have a dominant pole, what is the advantage it offers? Let us look at that quickly. That will help us in further Opamp discussions also. So generally, you might have studied the step response for a feedback system as well. So in a step response, analytically, we can show that the stability of the step response also determined by the uh, phase margin that you get. Uh, so let us see what is the definition of phase margin. I think briefly we had discussed this earlier, but let us recap the frequency response, and then based on that we will discuss the phase margin. And yes,
this we have not covered, like a step response and feedback we have not covered. Like
feedback, and you have covered the control systems, right? Control systems, so both of you have covered.
We have control systems in our third year, so we've just completed
Okay.
our
Oscillator you have not covered, or Burke-Hausen stability criteria for oscillator.
But yeah, that we have done. So, and we did a few oscillators. That's in our.
Yeah, so this concept is clear, right? This thing is clear. Mod A should be less than 1 at omega 180 degree. That means or basically 360 degree rather. So the frequency at which the loop phase shift is becoming 360 degree, at that frequency, the omega should be less than 1. Sorry, the gain should be less than 1. That you have studied?
That is for stability, right? But
Yes.
we have.
So let us, yeah, phase margin, gain margin, you might not have studied. So let us look at that. So we have discussed earlier that in a two-pole system or a three-pole system, how do we plot the phase and the magnitude response? So let us plot both of them, phase and the magnitude. So if it is a two-pole system, I hope you remember based on our previous discussion, this is how it looks like. After a second pole, my first pole you get 20 dB per decade, and after second pole you get minus 40 dB per decade. And likewise, we had studied about the phase shift. This is A, and this is your phase shift. So at 0 omega, whatever phase shift you are having for the amplifier, suppose in this case it is 0 degree, and then exactly at the second pole, how much do we get? Exactly, we get additional 45 degree minus, and then after significantly higher than you go the frequency significantly higher than the first pole, it saturates at minus 90 degree. So this one is minus 90 degree. And then we had also discussed that after the second pole, this is a strange artifact that I am getting this dot 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 thing. Anyway, so at the second pole, we get almost additional minus this 45 degree, and then at uh, much as the frequency is much higher than the second pole, we get close to 180 degree. So this is the phase plot and the magnitude plot for two pole system that we have studied. Is that clear to all of you? Do you remember all this?
Yes, sir.
Now in this case, how do we define as the phase margin? The phase margin is the point in the frequency for which, just a minute, my pen's cap dropped. Yes. Yeah. So the frequency at which the overall gain is becoming unity. That means your gain started from A naught and it is degrading after first pole and second pole. So suppose you have a particular frequency where the omega is becoming the gain is becoming unity. That means 0 dB. In terms of dB, it will be 0. Now at that point, if we had the phase, we need to see that at that point what is the phase value. So at that point we see what is the phase. So this is say omega phase at omega 0 dB. And if the phase, suppose, is already, it has reached 180 degree, that means at omega equal to 0 dB, your phase margin is very less, because maximum, the condition was that you at the omega 360 degree, that means your overall loop phase becomes 360 degree. At that point, the gain should be greater than 1. Sorry, less than 1 for stability. Now you're looking at the frequency at which the gain itself has become 0 dB. At that frequency, if your phase is already 180 degree or lower than that, that means the overall phase shift is 360 degree or more than that. That means at a higher frequency itself, the overall phase shift has become 360 degree. So suppose the phase plot was, I'm drawing an imaginary phase plot in this case. Uh, suppose the phase plot was something like this, and we say that at omega equals 0 dB, your uh, phase over here is, suppose it has reached say 135 degree. So if it has reached only 135 degree, then how much margin, additional margin, do you have at this omega 0 dB so that the system remains stable? So system becomes unstable if for gain 1 or gain 0 dB, your overall phase margin of 180 degree over here is achieved, which means overall phase shift of 360 degree is achieved, right? So in this loop, we see, but that's what we're looking at, that already you have 180 degree phase shift because of the inverting terminal. So we need to see at what frequency the phase shift from this positive input to the output is actually becoming 180 degree. So that's what this phase plot is showing, that at what frequency it is going closer to 180 degree. So now if we see in this particular plot, the way I have drawn, at omega 0 dB, you have a phase shift of 135 degree, minus 135 degree. That means you have additional margin of 45 degree, right? So that becomes your phase margin. That as compared to the uh, phase overall phase shift of 60 degree, how much margin I still have. Is that clear to all of you? This is the phase margin. You can define it as the phi, I would say phi at omega 0 dB, 180 degree minus, in this case, because this is a non-inverting amplifier. So what I'm seeing is that as compared to 180 degree, how much is the phase shift at omega 0 dB? So that gives me the phase margin. This is the phase margin. Is the concept clear? Like why we are calling this phase margin? Because you have that much margin with respect to phase. If your phase at this point goes lower by more than 45 degree, then you will be in trouble, because if the phase, suppose I draw it in another color, if I say that the phase was like this, that at omega 0 dB the phase is already lower than 180 degree, that means that the point at which it had reached 180 degree, at that point your gain was greater than 0 dB. That means the system is unstable, right? So that is the condition we are applying for stability. So how much margin you still have for more phase shift at omega equal to 0 dB. Is that clear to all of you?
Yes, sir.
So now, if you look at the overall uh, phase response, we target a phase shift overall of, say, we target a phase margin. A good phase margin would be, say, 45 degree or 60 degree. A 45 degree phase margin basically ensures good step response, and that again based on your S domain transfer function in Laplace transform, you can prove that analytically, if you are giving a step response to a feedback system, if you are having a phase margin lower than 45 degree, it will have this kind of ringing, because lower phase margins means it is becoming more unstable. If you go lower than 45 degree, say 20 degree, 10 degree, this ringing will further increase. It is still not stable. It is still not unstable. It will not lead to sustained oscillation, but it will lead to some kind of damped oscillation if your phase margin is reducing from 45 degree and below. So in order to get maximally flat response, we target 45 degree phase margin. Now, in order to get 45 degree phase margin, what is the condition? In this case, I've already drawn that condition. So I have already put a 135 degree phase shift at the omega 0 dB crossing point, and that essentially means that phase margin is 45 degree. So here you can see when this condition will be achieved exactly. So when you're when you want a 45 degree phase margin, what is the condition for that in terms of poles,
The
in
gain at
terms of pole
second pole.
locations?
So gain at the second pole, if it's 0 dB, then it will match, right?
Gain at the second pole should be 0 dB. So what you're saying is 0 dB should be 0 dB gain should be obtained at the second pole, or maybe lower than that, right? As long as the 0 dB omega 0 dB is, if it is less than omega p2, this is the second pole, less than equal to. If it is exactly equal to omega p2, then you will get exactly 45 degree. If it is less than that, you will get better than 45 degree. So that we can see here also. So we have just seen that at the second pole, we get a overall additional shift of 45 degree. So just before or before the second pole, when we are in between the two poles, this is P1, P2, omega P1, omega P2. So in between the two poles, after crossing of the first pole, we are at 90 degree. And when the second pole approaches, exactly at the second pole, we get a minus 135 degree. This is again, I have modified the plot. So let me draw it afresh. So this is just for explanation. I had drawn it slightly, I had overwritten certain things. So actual scenario is that at the first pole, you achieve a minus 45 degree. And then at the second pole exactly, you achieve another minus 45 degree. So this is minus 45. This is minus 90. This is minus 135. And then ideally far away from, as your omega approaches much higher than omega P2, which is here, omega P2, omega P1, omega P1, omega P2. So when your frequency becomes much higher than omega P2, then it asymptotically approaches 180 degree. Ideally, in the response, it will approach 180 degree. It will never, if you have only two pole systems, exactly two poles, no more than that, then it will never actually hit 180 degree. Asymptotically, it reaches 180 degree. That is the idea. So now, in this case, when if your gain plot its omega equal to 0 dB, it lies exactly at omega P2. That means the 0 dB gain is obtained at omega P2. Then we can say that we have exactly 45 degree phase margin, because till from that point we still have additional 45 degree available. We can afford to degrade the phase by additional 45 degree. Therefore, we have a phase margin of 45 degree. That is tells us that separation between omega P1 and omega P2 is important. If omega P1, omega P2 are coming very close, right, then it will create problem. So that means if you're in terms of say the magnitude gain magnitude plot, sorry, in terms of gain magnitude plot, if I look at it, if my gain magnitude plot, it is hitting omega 0 dB with minus 20 dB per decade slope. That means this is 0 dB and this is omega 0 dB. So if my gain magnitude plot is hitting omega 0 dB with minus 20 dB per decade slope, what does that mean? That the second pole has not been encountered yet. Second pole is way beyond omega 0 dB. So if that is the case, then we say that the first pole is the dominant pole. This is the omega P1, this is the dominant pole, and the second pole may be beyond omega 0 dB. So this omega P2 is coming somewhere here. So in this case, the circuit will be in the closed loop, the circuit will be stable, unconditionally stable without any problems. So that is the advantage of having a dominant pole in the circuit. So in a operational amplifier, when we are having multiple systems, multiple poles in the circuit, in the signal path, in the feedback loop, if we are able to ensure that there is a dominant pole, which is going to make sure that it is much lower than other higher frequency poles, and that the gain magnitude plot is going to hit 0 dB. The gain is going to hit 0 dB with minus 20 dB per decade slope. That means we have a stable, we are going to have a stable loop response. That is the key benefit of having a operational amplifier with a dominant pole. So that's why this topology can be useful. So it doesn't have a lot of stability problems. Is that clear to all of you?
So, but then we're limiting our bandwidth, right? If we have a dominant pole.
That is again a trade-off. So if you have to reach stability, you have to sacrifice bandwidth. And remember that this is only the open loop bandwidth. When you connect the feedback, if you have studied the feedback concept, I hope you remember that you get 1 plus A beta enhancement in your bandwidth also in the closed loop system. So this is only bandwidth of open loop, but bandwidth of open loop times the 1 plus A beta factor gives you the open closed loop bandwidth. So definitely open loop case, you are making a dominant pole, and that is definitely limiting the bandwidth also. But the actual bandwidth requirement is from the closed loop response. So we need to make sure that this closed loop, whatever we are having. In this case, beta is 1, right? So if it is a voltage follower, beta is 1, and therefore A, if the A is large, your overall this bandwidth enhancement will be large. Is that clear? So this is another important thing that we should note, because some other topology that we will study, there this advantage is not there, and we need to basically look into some other schemes, compensation techniques to ensure this kind of stability. Another thing that you should also look at is a gain margin. So I have given you the definition of phase margin. Gain margin, see, conditionally, if you, theoretically, if you see, if you read textbooks, you will find that you will find statements like two poles systems are unconditionally stable. So if you have exactly two poles in the system, the amplifiers will be unconditionally, the feedback system will be unconditionally stable. That means you are trying to make a feedback system, there's a feed forward path, and then you are putting some beta feedback, and then you are subtracting whatever negative feedback. And then in this entire, for analyzing the loop, we break the feedback, right? So we break the feedback at one point, and then we see from the starting point till the end point what is the phase shift. So in case your overall phase shift is, for omega dB, the condition over here is that for omega 0 dB, the phase shift should be, less than 180 degree. Another way of looking at stability is that uh, if your omega has, basically the phase shift has reached 180 degree, at omega 180 degree, what is the gain? So if I look at, say, suppose, in this plot, so that you can understand that in a two pole system, it is never going to reach omega 180 degree is never ideally achievable. It is asymptotically going to go to 180 degree, right? So that part you understand, because we have looked at the phase response also, right? So if you are having 1 upon S upon P1 and then 1 plus S upon P2. So at frequencies, we assume that at omega much greater than P2, both the terms becomes basically the second term also contributes to 90 degree exactly. So that exact 90 degree is possible when your omega is much greater than P2. Exactly means speaking omega is infinite. So ideally, that is when it is going to come exactly to 180 degree. Otherwise, it will always be slightly less than 180 degree. So for exactly two pole system, the phase will never hit 180 degree. It will always be slightly smaller than that at any finite frequency. So with that argument, we can say that as compared to multipole system, in the whole set of multipole system, up to two pole systems, the feedback amplifiers are going to be unconditionally stable. But still, for the two pole systems, if you are sure that the amplifier closed loop has only two pole systems, even in that case, this transient characteristics, this ringing will become more prominent as if your phase margin is lower. So for that, we need to make sure that your phase margin of 45 degree is still achieved. You have a decent phase margin. In case you have additional poles, you have multi-pole systems. After second pole, you're also having third pole, and the phase plot is further going down, right? So definitely at one point it will reach 180 degrees. At a finite frequency, it is going to reach 180 degree. And at that point, we need to see what is the gain. So now if I see with at this omega equal omega 180 degree, what is the gain? So this is your value of gain A at omega 180 degree, and how lower it is as compared to 0. So if it is higher than 0, that means you are in trouble. So gain margin means at omega equal to or omega 180 degree, the point which achieves 180 degree phase shift for the open loop response, how low the actual loop gain is as compared to 0 dB. That means how much more you can increase the gain at that frequency and still remain stable. That's why this is called gain margin. So gain margin means at omega 0 dB, whatever is your overall gain, and in terms of dB, you can say below 0 dB how negative it is. in terms of unity gain, you can just say that, okay, as compared to unity, how low your gain is. That is given as the gain margin. So gain margin generally, it is used less frequently in the stability analysis. Most of the time we use a phase margin, but still definition point of view, you should be aware of the gain margin term also. Is this clear? Both the concepts of gain margin, phase margin?
So we said two pole is always stable because our 80 is reached at infinity. So, but then if we have a 1, 0, and 3 poles, then also it will be like stable, right?
So zero again is a zero location. If you are having zero location coming after the second pole, then again it can create instability because zero will lead to basically, it depends on the location, right? If the location become very close to the second pole, then once again the phase, depending upon whether it is right hand half plane zero or a left half plane zero. If it is a right half plane zero, it will be coming with a minus sign. It will reduce the phase. If it is a otherwise the opposite case, it will also increase the phase. Phase becomes positive as well. So it depends upon the location of the pole with respect to zero. Sorry, location of the zero with respect to the pole, and how close it to the second pole. So if you have, suppose, 1 plus s upon z1. Now this 1 plus s upon z1 in the numerator, and then you have 1 plus s upon p1 and 1 plus s upon p2. Now it depends upon how close z1 is with respect to p2. If z1 is much higher, and by that time the phase response is already very close to 180 degree, what will z1 do? Now at omega much higher than z1, this term is going to contribute another 90 degrees. So phase may again go back to 90 degree, and gain slope will also reduce. So in this case, what will happen? Your phase, let me choose another color, maybe this one. So in case of zero, your phase in this particular case, suppose you get a zero here, zero. So in this case, what will happen? The phase will again go up, and much beyond zero, it will become 190 degree once again. And then your gain basically has, because of this zero term, you are getting increasing gain as well. So the after this particular zero, the slope of the gain magnitude plot will reduce. So if you look at the uh, overall gain, it is still dropping. Only thing, it is dropping with a lower basically slope, whereas the phase has gone positive. So in this case, it will not be creating trouble. Other case, if you have negative 1 minus s upon z1, now this is contributing negative, right? So now it will, what it will do? Suppose at this particular point you didn't have the third pole, but you still have just the zero. So because of zero, once again it will have actually more damaging effect, because let me use the third color, maybe this one. So this is the case, uh, this is the case where you are having the zero term, and it is 1 plus 1 minus s upon z1. Now it is going to create shift in the negative direction. That means even without the second pole, sorry, even without the third pole, because of the zero, you are getting a phase which is going beyond 180 degree. And then the magnitude plot has also basically falling with a smaller slope. So after the zero hits, the slope of degradation of the magnitude plot will also be lower. So if it is already below 0 dB, it's still okay. But if the zero becomes closer to the upper two poles, the omega p1, omega p2, then you can understand it may create problem. This 1 minus s upon z1 will create problem, because it is going to make the phase more negative, and it is going to reduce the decay of the gain. So 1 minus s upon z1 is a dangerous factor, not so much for the 1 plus s upon z1. So when you have zero, if you assume that zero, it is a much closer to omega p1, omega p2, then we need to look at the zero response as well for stability. Is that clear?
Sir,
Yes.
sir, so here to ensure the stability, we need to make sure that the zero crossover, sorry, gain crossover frequency should be much less than the second pole frequency, right? So now we
Much less
can't.
than, or even if it is exactly at the second pole, we get 45 degree phase margin.
Yeah. So here what we need is the second dominant pole, right? We can't go for the dominant pole in our analysis.
What do you mean? So if your dominant pole is much lower than all other poles, right? So that means that other poles, your overall gain, as long as this characteristic is obtained, that your overall gain slope minus 20 dB per decade slope is maintained till the second pole, then that means you are stable. So first thing is the condition for this will be that in order to make sure that it is stable, you need to make sure that first of all there is a dominant pole which is going to be much lower than your second pole. So in terms of magnitude, also you can understand that uh, what is the overall slope. So you hear the slope is 20 dB per decade, right? So 20 dB per decade, and therefore in one decade it is going down by 20 dB, and we want it to hit 0 dB by the time it reaches omega p2. So if I say that okay, omega p2 upon omega p1 log 10, this is going to give you how many decades have passed between omega p1 and omega p2. So what is the number of decades of frequency between omega p2 and omega p1? So what we want is that if your open loop gain without the feedback, whatever is your open loop gain, that is a naught. In terms of dB, you can say whatever a naught, a dB, whatever. This is the dB gain. So in terms of the gain, by the time you hit omega p2, your gain should drop to 0 dB. That means it should become 1. From a naught at low frequency, it should hit 1 before you go to omega p2. So that means here, if I take this in dB, whatever ADB you have, so depending on number of decades, so here you have this number, this thing is giving you number of decades. So here uh, we know that between these two plots, it is going to, between these 2 points, omega p1 and omega p2, it is going to maintain 20 dB per decade slope. And in terms of overall gain available, you have ADB. That means the low frequency gain is ADB, and therefore this divided by number of decades will tell you that okay, means whether with this divided by 20 dB will tell you that okay, how many decades you want to have, how many decades of gap you want to have between omega p1 and omega p2. So if we say that omega log of p2 about p1 is less than this, is greater than this, so ADB upon 20 dB, that this is going to ensure stability, right? So whatever is your 0 dB gain, sorry, whatever is zero frequency gain divided by 20 dB gives you the allowed, or basically the number of decades separation required between omega p2 and omega p1. So of course we need to look at both, but the moment we make sure that your a naught, the first pole is much lower than the other poles in the circuit, it is having a much higher possibility that this condition will be met. Is that clear?
Yes, sir. Yes.
Yes. So this is basically going to clarify. This is clarify that okay. What? Yes.
Sir, also now we cannot use the Miller effect while doing the frequency analysis, right? We need to check for the zeros also, whether they are in between WP1 or WP2 or less than WP1.
Zeros in this case is not going to be in this particular circuit. Actually, zeros are not very significant. So there are other configurations wherever we will discuss the cases where you have zeros. So zeros come when you have additional capacitances exerted in the path, like feed forward path. So feed forward path means whenever you are having a strong, basically feed forward path emerging along with the actual signal path, that can create zeros. Like suppose you are having this CGD, and that is actually responsible for creation of zero many times. Why? Because the mechanism is that here it is propagating the signal in the non-inversion way, non-inverting way, whereas this path is propagating signal in the inverting way, and therefore if it cancels out frequencies at which these two signals become equivalent, it leads to zero. So that is the mechanism for zero. So whenever you have this kind of paths in the circuit where you have a possibility of cancellation between the feed forward and the actual signal, then you may result in zero. In this particular circuit, actually, you don't have that kind of configuration. It is CGD here in this case, it is not very high. We will look at some other configuration where we intentionally insert this capacitance to make the circuit more stable, but as a byproduct, it also gives us 0. So for this condition of achieving this stability and having this omega P2 much higher than omega P1, making sure that the omega 180 degree exactly at omega P2, in order to make sure we actually insert this kind of capacitance, uh, that in certain cases will create zeros also. So when you are having additional feed forward path inserted in the circuit, it leads to zeros and stronger zeros that we need to address in the response. For the time being, in this circuit, you don't have such a dominant or basically significant zero. We will look at the zero case in one of our following configurations. So I hope this is clear.
Yes, sir.
So this gain margin, fade margin, you please take note of this. Very, very crucial. And for whatever amplifier, etc., we design, this analysis is extremely critical. Without that, feedback amplifier is not complete. Design of feedback amplifier is not complete. This is one of the key things. Okay, so let me see whether I want to talk about anything else regarding this amplifier. Voltage swings, etc. I hope you are, based on your single-ended discussion, you can do that very easily. Input allowed input swing and output swing based on the transistors, gate voltages that you can find out. Another thing, in terms of systematically analyzing, so the way I described the gain, I also should describe the poles. Like, we have to follow the signal, like how the signal is propagating in the circuit. So in this circuit, I described to you the signal path overall, how it is flowing, right? So if I use a red pen, so we say that, okay, you have GMVGS created by this. So you have small ID1, suppose produced by this one, same ID1 comes here. From your current here, the same ID1 comes here. And then this is also having ID2 because of the VGS2, and that ID2 is coming here, and that is mirrored into this one, and finally it is coming to the output. So both ID2 and ID1. Now, if you look at the signal paths, so from the first input, the signal is flowing in this direction, right? So you are having signal path for the first signal, for the first input. Second input, the signal is flowing in this direction. So the signal paths from the negative input to the output is different. Signal path from the positive input to the output is different. If we assume that this is AC ground, and assuming that this becomes like a common source amplifier, and we find out the overall gain transfer function, right? So gain transfer function from the first input to the output and the second input to the output, they are not identical. They are different. In magnitude terms, we can still say, if you just look at 0 dB, sorry, omega 0, or basically DC gain. For DC gain, if you ignore all the capacitance, etc., in that case, the magnitude definitely will be aligned, because here what is happening is whatever small signal current you are producing. Suppose you have the signal here is VD by 2 or minus VD by 2, and this is VD by 2. VD is the differential net differential signal, and plus VD by 2 on the positive terminal, minus VD by 2 at the negative terminal. Just for the sake of definition, we are saying that there is a differential signal, and whatever common mode is there, that is eliminated, that is suppressed. So here you have VD by 2 minus VD by 2 on the two input terminals. From plus VD by 2, the gain will be given by this common source stage, first given by M2 and M4, and second is your cascode stage. And for the second VD by minus VD by 2 applied at the gate of M1, the first stage gain is again this common source stage, which is composed of M1 and M3. And then there is a second common source stage once again, which is composed of M3 and M8. And then you have the third, the cascode amplifier. And there also it is input is the GM9, basically. It is different from the GM6. So definitely we can see that overall the magnitudes may be similar, but the number of poles, etc., in these cases are different. Of course, what we see is the current magnitudes are same, even if you are having GM6 in this case and it is GM9. So we can find out the overall transfer function in terms of all these GM and RO, and then we can see that ultimately the magnitude of the gain will be same. Can you do that? So if you find out, say, path 1, I call this path 1, I call it path 2. So what will be the gain of path 1? So let us quickly write it over here. Path 1, what is the gain overall? How do we find out? So see, path 1 is common source. First stage is common source. Second stage is also a common source. Both cases it is a direct connected load. And finally, the third stage is the cascade. So for path 1, what is the expression? It will be A1, A2, A3. Three stages are there. What is A1? Quickly, quickly. Assuming that is AC ground.
So GM1 by GM2.
GM2.
GM3s.
GM1 by GM3. Because you have M1, M3, which is a direct connected load, common source amplifier with direct connected load. So GM1 by GM3. What is A2? No, sorry. Wait a minute. What have I done? Actually, you were correct. It is 2. I have numbered it. No, this is 1, 2, 3. So actually, I have numbered it incorrectly. It seems 6, 7. This is supposed to be some other number. I have made most of them 3. So wait a minute. If I call this, if I keep it 3, 4, 5, 6, 7, 8, 9, 10, 11, make it 12. What it can we do? Because by mistake, I have made both of them 3. So make it 12. Okay, now you tell me. Second stage, A2.
GM12 by GM8.
GM12 by GM8. And now, of course, we can see that if your 3 and 12 are, if your GM3 and GM12 are similar, because sizes are similar, bias currents are similar, in that case, they will be cancelling out, right? So now let us see next stage. What is the gain? This stage. Remember, this is the same cascade stage. So we have discussed this earlier. So this is simply input signal. If it is V in, GM V in is a small signal current produced, but then we get some current division also. Remember that part of the current goes into this RO of this downward MOSFET, and then only a part of it goes up. So 1/2 factor comes into picture, so that we can include. But the gain is given by GM of this transistor GM9 into the whatever is output impedance. So that is GMRO square, of the order of GMRO square. Exact value will be GM11 into RO11 into RO6, and then likewise GM9 RO. So overall you have GMRO square by 2. So you are getting a impedance. If you look at the overall, if I assume that the upper and the lower path, both of them are having similar GMRO, in that case, it will be for the input path. For this path, it is GM9. Then 1/2 factor comes because of the current division. And then that current goes into this path and multiplied by the impedance of this upper branch. What is that impedance? That is nothing else but GM11, RO11 times RO6. Right? So that's why overall we get GMRO whole square. And this is assuming that GM9, GM6 are similar, and likewise GM11, GM10 are similar, which can also be slightly different. It's not necessarily that they will be exactly same. Here also we can see that GM8, GM9 may be similar. So in that case, magnitude point of view, we can cut it because they are mirrors and they are having exactly same VGS, W by L. So GM will be similar. Likewise, 12 and N3 it will be similar, right? So here also GM12 and GM3 will be similar. So ultimately, it will be GM1, and then you will be getting the GM9 will also getting cancelled. So it will be GM1 into GM-RO square by 2. Magnitude point of view, if I assume that all these transistors are well matched, we still get almost similar magnitude for both the paths. Second path, what will be the expression? If I say path 2, you are having only 2 stages. I mean, first is your common source stage, which is going to give you GM2 by GM4, right? And second stage, once again, GM6, which is same as GM4, which will get cancelled by GM4 into wait a minute. So it is basically getting cancelled by GM4 multiplied by whatever is the impedance. So 1/2 factor will come, and you multiplied by GM-RO square impedance will come. Same thing, this gets cancelled. GM2 comes into picture, and GM-RO square comes into picture. Remember, this GM-RO square is different. It is not exactly same as the first path. So we can see that if there is, it is can be possible that even your magnitudes are different for the 2 paths. But assuming that the transistors are well matched, magnitudes are similar, at least the overall amplitudes, overall gain magnitude for the both paths are similar. But what about the poles? So in both the paths, are the pole equal in number, or are they different? So first path, you see how many poles? First pole is this node. Second pole may come at this node. Third pole at the output, right? So this is a signal path. And out of these, this is a high frequency pole because this is lower impedance. This will lie at highest frequency. After that, this one, and after that, the output pole at the lowest frequency. Likewise, for the second signal path, this is going to be at low frequency. This is low frequency pole. Sorry, this is going to be at higher frequency because low impedance. This pole is also at very high frequency because it is low impedance node. Therefore, these two are not playing much role. And then finally, you have this node and the output node once again coming into picture. These two nodes, they are also slightly different. They are not exactly same. These two nodes are also slightly different. But if I assume that the dominant pole is only this one, out of all these other poles that we are getting, the dominant pole is this one. Approximately, we can say that the gain is still A0 upon 1 plus S upon P1. Other terms are, non-different. Other terms are much higher than that. So that is approximation we take for the amplifier where you have a dominant pole. Other than that, of course, we have other poles coming into picture, and the two signal paths are different. If you want to do the exact analysis, it will become you will have to basically combine the two paths, right? So if you say first path is having A1, A2, A3, and we saw there are multiple poles, 1 plus S upon P1, 1 plus S upon P2, and 1 plus S upon P3, and P1, P2, P3. P1 is the first diode connected, first stage load. This is the second stage, which are also at high frequency, and P3 is at the output stage, and another one is also coming, 1 plus S upon P4, which is the load. This is the output one. Others are lower than that. These two are because of the diode connected load. This is the overall expression for the first path. And second path, you have a different transfer function, which is maybe A1 dash, A2 dash, which is different. It may be slightly different from A1, A2, exactly not matched with A1, A2. And then you have 3 poles, 1 plus S upon maybe P1 dash, 1 plus S upon P2 dash, and 1 plus S upon P3. P3 is same because it is I would call it say P4 because that is common. Output node is common for both the paths. That is same. And then you have P1 dash, P2 dash in the second path, which are also possibly different because this is for the diode connected. So this is because of the diode connected stage. This may be similar to P1. This is very close to P1. So I can say that these two are common. This P2 is similar to P3 over here. So rather let me call it P3 dash because if you look at the second path, what is happening? Second path, you actually have the first pole is over here, diode connected load, giving you first pole. Second pole at this point between the first PMOS, second PMOS in the cascode stage. This is also giving you another pole, and third pole is this one. So this one is similar to the pole offered by the M9, right, at the brain of M9 for the first path, whatever pole you got at the drain of M9, the second path also gives you similar pole over here. Therefore, I'm calling this as P3 dash, right? Because it is similar to P3 of the first path. This will become P3 dash. So out of these poles, what we see, if we assume that the transistors are well matched, so I can say P1 dash are similar, P3 dash are similar, P4 are similar, but you have this part which is not existing in the second path, right? So this path is different. Now, if you have to find out the output signal net, what do? We take the superposition, right? So overall, V out will be V in 1 into HS1, whatever is the first transfer function, plus V into HS2, second transfer function. Therefore, we have to add up these two. If you add up these two, now again we can assume that A1, A2, anyway, we are getting similar magnitude. A1, A2, A3 multiplied together, A1, A2 multiplied together, similar magnitude. So we can take it common out, right? And that basically becomes our GMRO kind of. This will become GM RO whole square by 2. And then you have these poles. So in the pole, what will you get if I assume that these 3 poles are common? So they will come as it is, 1 plus S upon P1, 1 plus S upon P2, 1 plus S upon P3, 1 plus S upon P4. But the one which is not common, it will lead to a numerator term, right? 1 plus in the numerator, it will come. So here you will get 1 plus 1 plus S upon P2. So this is also giving you some kind of zero term, right? So that also we should see that, because of your mismatch in the transfer function, the non-equivalent transfer function, there also you are getting a zero term created in the numerator. So this is, again, this is also not exact analysis. This is also approximate analysis, but this is also giving us some zero location coming because of. Now the P2 pole is because of the diode connected load. That diode connected load is again a very low impedance node. Therefore, this zero is also lying at a very high frequency. So we will, for the normal analysis, we will ignore it. We will say that this zero is also at a much higher frequency, and the dominant pole is P4, which is much lower than all others, P1, P2, P3, P4. Is that clear to all of you? So this is just to show you that, okay, in a circuit like this, how do we do the frequency response? For a single stage amplifier or multi-stage amplifier, I have already discussed. But here we have a differential amplifier where the two paths are not symmetric. We need to follow the signal path and then figure out the frequency response for both the signal paths, and then add them together and figure out what is the overall frequency response. So this is the, I would say, more exact way of analyzing the frequency response. Of course, when we design the actual circuit, we know that, okay, this is the dominant pole at the output, and we just want to make sure that it is much higher, much lower frequency as compared to the other poles, and we are happy. We don't worry about all other lower poles. But we should be aware of the exact analysis as done in this case. Is that clear, all of you? Any question on this? I hope this half circuit, the signal paths are clear. Path 1, path 2, both are clear. What is happening?
Yes,
Any
sir.
question? So here, all we have done is you have broken down into half circuits. Half circuits, you have in the first path, you have 3 stages. First stage is a common source amplifier. Second stage also common source amplifier. Both are direct connected load. And third stage is a cascade amplifier. All these things we have studied earlier. All I have done is combine the overall transfer function for both the paths. So it is important to basically be aware how the signal flows in this circuit from the input to the output. That will also help us in getting started with the second topology. This same analysis that we have done, it is also applicable to the second topology. So let us look at that. So before you go there, any question before we switch and go to the next? Another thing that you can look at is DC bias, right? So DC bias, when we now you can say this is also single-ended output. So how do we make sure that the output is going to have a proper DC bias? So how will we do that? What is your answer? What we said in the common source amplifier, if you use this stage, like this cascode stage standalone, it is very difficult because you can't have a DC bias at the output. But here, why are we going to use this? How are we going to use this operational amplifier? How is it making sure that there is a stable DC bias? Because it's a very high impedance node. Output is a very high impedance node. So how do we make sure that you are going to have a stable DC bias? Yes, any idea? Say something.
Like so current mirrors, we said that DC biases like
Like what? So here we are talking about output node. So first stage, there is no problem. It's a diode connected stage. So that is not a problem. Here, this point is also not a problem because, here also, this is not a problem. This is not a problem. This is not a problem. Problem is this. This is output stage, the output node. So this is very high impedance node that you understand from our previous discussion. How do we make sure that this is having a proper DC bias? That is the question. It's a silly question and a silly answer, but think about it. Hint is this circuit. I've given you the answer.
so like do we like in the feedback one?
What feedback one?
Do we just bias them together? Like we bias the inputs and output together, like the
What do you mean by biasing them together?
like so like we this one.
So the diode connected load at input is ensuring its bias point, right? So when we connect the feedback, it ensures the output bias point also.
Feedback to what? So
We
your
are
answer
connecting
is. So what does it have to do with the diode connected load? Well, the answer is that in the closed loop, the negative feedback takes care of the DC bias. The negative feedback itself will establish the required DC bias. Why? Because what you are doing is you are connecting this particular point to the negative input, say, from the voltage follower configuration. So now if you see, you have put some DC bias over here. V in DC, you have VDD, suppose 1.8 volt, and you're putting, say, at this point, you're putting 0.9 volt. Now, what will happen if the input of the gate M2 is 0.9 volt? You can see what will happen to the other, because you have a negative feedback. So assume that it is slightly different from 0.9. Suppose it is 0.91. So what will happen? So if it is 0.91, that means it is slightly higher than this. That means what will happen to the currents? Which current is going to be higher? Whether the output is going to go high or low? What will happen? So if this is 0.91, we can again trace. We can figure out the current in M3 will be higher than current in M4. Let me change the color. So the current in M3 because of this 0.91 will be higher than M4, and as a result, you just space it back. The current here will be higher than the current coming from the upper PMOS. So whatever is coming from M6, as compared to that, the current in M9 is higher, and therefore this voltage is going to go down. It will try to pull it down. So basically, it will try to reverse it back. Whatever polarity change it experiences, because of the negative feedback, it will push it back to the same point. Or in other words, you can also look at the V in. If you are if you are changing the V in plus by any small value, 0.05, Same thing will happen. If this goes up, the same effect will happen. The current over here will be higher. The current in the M9 will be lower. Output over here, it will therefore go up. And till what point it will keep going up? Till what point the current differences will be maintained? Till this point becomes again exactly equal. Only at that point the small signal currents will basically cancel out and settle, right? That part is clear, that how the small signal current flow is going to make sure that this terminal tracks the DC potential at the input. Is that clear? The moment you apply a step change, 0.9 at this gate to 0.05, 0.95. So how this small signal current is initiated, you are going to have a larger small signal current flowing through the M2 and hence through M4, hence through M6, and as compared to the current in M9, the upper current flowing from the upper branch to the output is higher. Therefore, the output voltage will go up till the point these two voltages become exactly same and the small signal currents cancel out each other. Is that clear?
Yes, sir.
So I hope you are getting a feel that here in this case, what is happening, the DC bias is taken care by the feedback operation. So the operation, if you are operating this as an operation amplifier, whatever DC condition you're applying at the input, it is basically establishing the feedback at the output also because of this negative feedback action. So negative feedback is not only applicable to AC signal, but it is ultimately applicable to DC also. So this negative feedback helps in making sure, that's what we study in op-amp, right? That your two inputs are always going to be same, exactly same. Why does it happen? Because of this gain. The larger is the gain, the closer these two voltages will be, right? So because of this, small signal operation and the changes in the small signal current, we are seeing that the negative terminal voltage will eventually follow the positive terminal voltage, and hence the output voltage will follow the input voltage. This point is very, very important. You should be able to understand that how this following operation is coming, like why we say that this node is following the positive node. Whatever changes you are making here, this node is going and following that node. That you should understand by following the small signal current path, how the small signal currents are produced when the moment you increase the Vin plus to a slightly higher value, how are the small signal currents produced in different branches, why the current in the M6 is slightly higher than the current in the M9, and how it leads to the output going up. And if the output goes up gradually, till what point it will keep going up? Till there is a difference. The moment this voltage become equal, difference is gone, and therefore these two currents in the M9 M6 one again become equal, and then there is no further change. So then the voltage will be again settling to that value. Is that so? This point is very, very important for op-amp operations. You should understand this is how it is working. Any question on this? So in the single stage amplifier, when we study common source, there we don't have this facility, right? We don't have any feedback, we don't have any DC feedback. Here we have that, and therefore we can operate it with the help of this DC feedback. We don't need to worry about the output DC bias. Even if you put another stage, and take the feedback from here, right? So we have said that we will be putting a common drain. There also will study ultimately feedback will still ensure that the output of the common drain and the input DC is at the same point, and that will ensure that a particular DC potential is achieved at the output of the first stage. Yes, somebody was asking something.
So like if you are shorting V in one and V out, then like I didn't understand like how we are just copying the exact same signal, right? Then how are we getting any gain?
This is a voltage follower, right? That's what I guess is voltage follower. Have you studied voltage follower in your basic electronics?
Yes, sir. But like if we are trying to design a general op-amp, like for we're not
general op-amp also you will have feedback, right? So general op-amp means ultimately you will have some kind of feedback. Suppose you are putting a inverting gain amplifier. So what will you do? Rather than shorting it like this, you will put a resistor R1, R2 that will also establish DC bias. Let us draw that. Only thing is I have to draw that circuit again. It's a pain to draw the circuit so many times because it takes some time. Let me do that. If I had the option of copying, the problem is if I write so many things on the top of circuit that it becomes difficult to copy paste also. The only option left is that I have to redraw. So anyway, let me do that. So black color. So the first stage, I will draw very quickly. Don't think that will be the, and then you have the second stage. Anyway, the cascode. I am not drawing all the bias points. This will be having some bias. And you have the second stage and another one over here, and this. This is your condition, and this is your output. So this is your positive input. This is your negative input. For negative inverting gain amplifier, you put R2 by R1, and you put input signal over here, V in, and there is some DC signal over here. Whatever you put it AC ground, generally it will be some DC signal which is treated as AC ground. So that same DC will appear here. So only thing is, rather than right now, earlier these two voltages were exactly same, right? Because if you had just shorted it like this, for the voltage follower configuration, you were forcing V out equal to V in. Now, what is the case? Now the situation is that there is a voltage division from V out to this point. There is a voltage division in terms of DC. If I see what is the voltage division, so V DC, or I can call it V out DC. This is your V out DC. So V out DC into R1 upon R1 plus R2. That's all. So the principle is still same. I think I should not have even drawn this. Just with this circuit would have been good enough. So here what is happening? The condition is same. Only thing is, earlier I had made these two exactly same because of the shorting, and that was acting like a voltage follower. Whatever input you apply at the positive terminal, the same will appear at the output. But in this case, it is an inverting amplifier, and this is the relationship between the output DC voltage and the input DC voltage. So if I want, in this case, we are getting some conditions. You can't arbitrarily bias the input DC and output DC. So whatever is your input DC, it is dependent upon the output DC and vice versa. So you have to choose the input DC appropriately, so that based on the R2 by R1, you will be getting an appropriate input DC. That also tells you some constraint regarding the gain. Like if you want a very large gain, what will happen? R2 by R1 ratio will be very skewed, right? And the R2 by R1 ratio is very skewed. This voltage will be much lower than the out DC, and you need to make sure that it is proper, because there is some minimum allowed voltage, right? If you go lower than that, the tail current transistor will enter into triode region. So if you keep R2 by R1 very large, uh, first of all, the output DC will be required to be large. You will be forced to keep the output DC point larger and the input DC point smaller, because you are targeting large gain, and the ratio between the input DC output DC is going to be large. So in this case, if you use resistive divider, this is a disadvantage, that the DC bias will be constrained. Basically, the overall gain will be constrained by the DC bias. If you want large R2 by R1 gain, then the DC bias also has to be taken care of. Appropriate DC condition. If you violate the DC condition, if just because of putting large R2 by R1, your output DC is going too high, input DC is going too low, then eventually what will happen? The input side tail transistor will enter into triode, upper transistor will enter into triode, and you will not get a good gain. After that, the gain will fall. So that is also another constraint that you will face in designing feedback amplifier with resistive feedback. To mitigate that, people use capacitive feedback also, that we will discuss a little later. Capacitive feedback will not suffer from this kind of issue, but still, in that case, you need to make sure that the DC bias is established. So in that case, what happens? Just like in case of resistor, you get a R2 by R1 gain. In this case, it will be also the same. In this case, C1, C2, so it will be C2 by C1. That right? So in terms of small signal gain, it will give you the C2 by C1 gain. So the only problem is DC bias. So in this case, also the way people establish DC bias is that okay, the capacitive feedback will give me the AC gain, but then I will put a very large resistor over here, which is establishing the DC bias. So suppose I put a 10 mega ohm or even larger 100 mega ohm resistor. Now, this kind of special resistors can be made using certain techniques. We will discuss that. But suppose you have this kind of resistor available, you can make this kind of resistor using sub-threshold region transistors. We'll discuss that. It will take some time to discuss. But in this case, what will happen is the C1 by C2 ratio is not affecting your DC bias. It is basically independent of your DC bias constraint. So you can choose appropriate C1, C2 based on whatever gain requirement you have. And still, in order to get the DC bias appropriate, you put a very large resistor, just shorting the output and input. In this case, there is no voltage division. Whatever is your V out, same will be your V in, DC point of view. DC condition will be established by this R. And the small signal gain, this R is very large. And therefore, the small signal gain mostly is determined by the C1, C2, because 1 upon omega C will be much smaller than R. And therefore, you can ignore this R as compared to C1, C2. And therefore, the AC consideration will be given by C1, C2 only. That is the advantage of capacitive feedback. It doesn't messes up or does not conflict with the DC bias point of the actual transconductance amplifier. Is that clear to all of you? Yes, any question? Any question? Let me see how many people are sleeping, how many people are. So there are, I hope all of you are able to understand whatever is discussed.
Yes, sir.
Yes, sir.
Okay. So let us discuss the next topology. So I hope this one is clear. Advantage of this dominant pole is clear. That is clear. Those things should be very, very clear cut. And second thing that we discussed was the DC bias at the output with the help of feedback, and then capacitive feedback. Okay. Let us go to the second topology. I hope so. This is ending. Okay. So it does have a end of panning. So after that, it is not letting me pan further. I don't know what is this going to do. This is not. So this is the end of the page. Anyway, so in that case, I will start from the next page. All right. So now the second op-amp that you would like to study is based on current mirror load differential amplifier, and that is also going to help us in going towards the fully differential amplifier as well. Let us look at that. So the op-amp structure that we just discussed, it is based on the differential amplifier stage, where the first stage is fully differential. So in the first stage of this op-amp that we put, it was a fully differential amplifier, because for the first stage, you see in this circuit, ultimately the first stage is fully differential, right? It is differential input, differential output. But overall, if you look at the second stage, it is single-ended. It is folding the signal. It is called signal folding, right? So you're just like current steering, right? Current steering. So the input, whatever the small signal current is produced by the input stage, that is getting steered to the output state. That's what we say. So the current produced by the input is getting steered to the output state. Likewise, from this path also. So this is current steering kind of phenomena. So single first stage, if you see, it is fully differential input as well as fully differential output. Now, the other topology that which is very common and can be used for op-amp design is current mirror load, where you have circuit like this. I hope that swing, etc., I have covered in very quick pace. I did not, but I hope you've got the feel, right, that swing will be a problem, R1, R2 issue, DC bias, those things. If you're not understanding, please feel free to ask. Some things I'm going fast because we have to cover many topics. So in case any point is not clear, please feel free to interrupt. If you don't ask, things will remain pending. So this is the second topology. Here also I will do some quick analysis and try to figure out what is the small signal gain at the output, from the input to the output. And again, similar conditions, you have V in plus, for this stage, the V in plus is this. Or if you're talking about only the first stage, this differential pair, the input, positive input is M1 gate. Why? Because from here to the output, the gain is positive. If I add another stage, then it becomes kind of, it basically reverses the polarity. This becomes a positive input because you have two stages. That also you should take care of. Now here you have this one as a positive, V in minus as the negative. And once again, if I look at only the differential signal, so let me just look at the differential component and figure out what is the gain. So Vd by 2 minus Vd by 2. Now, if you're applying this Vd by 2 minus Vd by 2, and we assume that for the differential operation on this point is AC ground, we can treat these two once again as common source stages. So this is simpler than what we have already analyzed. Whatever we have analyzed, the two stages amplifier analysis here is similar and simpler than the previous one. So here, what do we see? So the small signal current produced by M1 will be what? GM1 Vd by 2. Same current goes into this one, and M3, M4 are following current mirror. Therefore, same small signal current will be coming in M4, which is GM1 Vd by 2. Whereas for the second one, it is minus Vd by 2. M2 gate voltage is minus Vd by 2. VGS, the small signal gate to source voltage, is minus Vg by 2. Remember, we are talking about small signal gate to source voltage, assuming that source node to be AC ground. So that also probably I will give you some assignments so that you don't confuse between large signal, small signal, and you understand the circuit behavior. So here it is. I hope those things are clear. Sometimes I also I feel that yeah, means if you do the simulation, it will be more clear. Means sometimes I've seen one couple of questions earlier which showed that yeah, you had confusion between the DC and the AC. Those kind of confusion should not be there. Right now we are talking about small signal AC, and for that this point is AC ground, and then we are doing a small signal analysis, trying to find out the small signal currents in different transistors. So for these transistors, and this is the M2. M2 is just going to give you current of GM2 Vd by 2 with a minus sign because it is minus Vd by 2 because it is a differential signal, plus Vd by 2 on the first one, minus Vd by 2 on the second one. And therefore, if I change the polarity, if I reverse the polarity, I can write it GM2 Vd by 2 in this direction. And now if I look at these two transistors, M4 and M2, so if it eventually what is happening, if I draw the small signal model of this, so you are having some small signal current produced by the GM2 Vd by 2 minus, right? And you have the RO of 2, RO2. Likewise, the drain of M4, you are also having GM1 Vd by 2 coming at the drain of M4. Why it is GM2 Vd by 2? Because ultimately you see the same thing will happen, right? So you have the small signal current here is GM1 Vd by 2, and the gain over here, if you look at the gate voltage, what will be the gate voltage? So from input to the gate voltage, say VG3, what is the gain? Gain will be simply GM1. The voltage signal at that point will be GM1 Vd by 2 into 1 upon GM3. Is that clear? Because from input to the output, we are looking at the signal. This is a common source. This is, for AC we are shorting it to ground. Therefore, the signal over here at the gate of M3, because of the first applied signal at the gate of M1, that is going to be GM1 by GM3 into Vd by 2. That is clear. This is just a common source amplifier with diode connected load. Therefore, GM1 upon GM3 into Vd by 2. That's all. And then because this is the voltage appearing at the gate of M4, VGS of M4 is this. This is the VGS of M4. Therefore, this into GM4 will be the small signal current flowing through M4. This thing. And because your GM3 and GM4 are same, I cancel it. And therefore, I get GM1 Vd by 2. So that way also you can see that ultimately the current in this one is GM Vd by 2. So you have some gate voltage coming. So I'm not drawing the gate of M4. I'm just drawing the drain point of M4 because gate, we know the story till the gate. Story till the gate is this. And at the drain, we are getting the current GM Vd by 2. That is the situation at the drain of. Here I'm not drawing the gate of M4 because we know what is happening at the gate of M4. It is producing the current GM1 VD by 2 in the drain of M4. And then also you will have RO4 over here. These two are connected. The drain of M4 and the drain of M2 are connected. Therefore, now here also, if I reverse this sign, so as we see that, if we reverse this sign, if I say plus means the current direction will now get reversed, right? This positive direction. So in this one, we have GM2 VD by 2, and you have GM VD by 2, which is basically also. So in other words, what I was talking about is you have an overall current flow, which is GM VD by 2 into the drain, the source to drain of M4. So this is GMVD by 2, and you had basically from the drain to source. So actually the earlier current direction was GMVD by 2, GMVD by 2 with a minus sign from the drain to source of this. And therefore, if I look at the overall current flowing through the combination of the RO4 and RO2, it is going to be the summation of basically these two terms, which is going to give you GM1 VD by 2 and GM2 VD by 2 together, right? So one of them is minus sign flowing downward, and then if you change the direction, it becomes upward, and then you have the GM1 VD by 2 following in this direction, and therefore overall current that goes into the resistance is going to be combination of GM1 VD by 2 from the M4 and GM1 VD by 2 from the M2, and that gives you basically overall GM1 VD, the overall small signal current into the output impedance, which is a parallel combination of this and this, which is RO by 2, RO2 parallel RO4. I can call it approximately RO by 2. So this is the overall gain, GM1 RO by 2 from the input to the output. So this is the differential gain AD for this stage. This is clear how the gain is coming. This is simpler than the previous stage. Previous stage we had more stages. Here I have tried to do the small signal model also, trying to show the current direction and how we can also do the exact analysis showing that okay, because of the VG, how much the small signal current produced, and then when we say that this current is flowing into the output impedance, what does it mean? Because ultimately the output impedance at this point is nothing else but RO4 RO2 parallel, RO4 RO2 parallel, and it is coming from this scenario, right? Because ultimately the drain of these two are together. The small signal impedance of RO4 comes between the drain and ground. Small signal impedance of M2 comes between the drain and AC ground. Therefore, they are basically in parallel, and therefore this is because this is AC ground, right? This is AC ground. Therefore, we just say that okay, this overall small signal current is flowing into the output node or output impedance, which is RO4 parallel RO2, and therefore the overall gain is this. Is this clear?
Yes, sir.
Previous one also we had done the same thing. Only thing is we had one more stage. Now this is okay. Again, we have done some approximations. That approximation basically including basically ignoring the RO of RO3, RO4 while calculating the small signal current. So when we just transferred the VG, we are ignoring basically the RO3 contribution, but they are not going to be very significant. So it is still okay. This is a simple analysis which is valid. Now, if you look at the second part that we also need to look at is the the common mode gain. The common mode gain, again, we will basically have the similar condition. We will apply the same DC voltage at the two gates. So they will be tied together, and we will try to sweep the input. So this one is diode connected, and if these two are connected together, this is connected to the VCM. So again, remember that when I am crossing two wires vertically, like this vertical wire is crossing this horizontal wire, there is no dot. If there is no dot, that means they are not connected. So when there is a wire like this, if I don't have a dot here, is not connected. Only when there is a dot, they are connected. If it is just like this, then it is assumed it is connected. But still, for clarity, I will make a dot here also. Like here, I have done it just to make it clear. Here also, let us keep the dots just to keep this convention uniform. So now here, if you are having perfectly matched transistor, that means M1, M2 are matched, and the two transistors upside are also matched. What is going to happen if the gate voltage are exactly same? Whatever is your ID, same ID by 2 goes into both of them, and if the same ID by 2 goes into both of them, the PMOS also has same ID by 2. They have the same source voltage, same gate voltage, only the drains are not connected. So if the same ID is flowing, ultimately they should have the same drain voltage also. Equal, and they will be tracking each other if you are applying the common mode voltage. Both voltages connected to the same value and sweeping up and down, the output DC potential of this stage will be same. Both the outputs will be same. This is not the output. Final output is this one. So what I'm saying is the drain voltage at both the sides will be same. Therefore, I can assume that this is also shorted, as effectively this is also like basically direct connected. So in the half circuit, when we combine the transistors, the upper load transistor appears like a direct connected load, and you have basically tail current source. So this one became 2GM1 because this is M1, M2. So combining together, it became 2GM1 as we have seen earlier. If you look at M3, M4, again, you are combining both of them. W by L is also basically increasing, double current is also double. Therefore, this also becomes same 2GM whatever 3. And this is anyway ID, providing ID. This is some gate potential. And now I need to look at the common mode gain. The VCM is applied here, and your output is over here. So here, what is the V out upon VCM? Yes.
2 GM into RO of the current source MOS, like the lower one.
Sorry.
Like so the RO output resistance of the lower third MOS, just for the current source. Like it's a.
What will come with the numerator?
Like this is like common source with regeneration.
Yeah. So what is the output?
I need to name the third transistor, like as RO of that, but which like
yeah, whatever. So there is no RO, right? The impedance looking upward is 1 upon GM3. So
GM3, yes.
So 2 GM1, the impedance looking upward in this case is just 1 upon 2 GM3 and 1 plus GMRS. So 2 GM1 into RS, which is basically RO of whatever you have 5. So 5, RO 5. Is that clear? And then approximately you can again, if you say, these are like GM1, GM2, of course, they are not going to be same. So, but from the point of view of order of magnitude, GM1 upon GM3, and then GMRO generally, it is much higher. So 1 upon 2 GM1 RO5, and therefore you get basically GM1 getting cancelled and 2 GM3 RO5. So this is the common mode gain. And therefore you can see as compared to the earlier case, this is earlier, if you look at the our previous cases where you had current current source load, fully differential amplifier with current source load and also resistive load, there the impedance on the upper side was also larger, and this is basically GMRD. In this case, the impedance looking upward is smaller. It is just GM1 upon GM2, and here you are getting overall the overall gain, which is the common mode gain, is getting 1 upon 2 GM3 RO5. Now here, if you look at as compared to the previous value, here the common mode gain is lower because the load is basically a direct connected load as compared to the earlier case where it would be RD or RO. So as compared to that, here we are having only 1 upon GM2 GM3, which is lower, and therefore we can say that the common mode gain is lower, which is advantageous. We want a lower common mode gain. And from the point of view of small signal analysis also, what we can see is the reason why the common mode gain is poor, again following the same current flow, the current steering behavior, we can see what is happening for the common mode signal. So if you're applying a common mode signal to both the gates, which are basically identical, suppose VCM, VCM, and both are going up together. If both are going up together, what will happen? This will be suppose M1, M2, M3, M4, M5. And here net output impedance is again RO4 parallel RO2. That's what we have seen. So now this GM1 uh, in VCM flows into this one, it flows into this one, and therefore GM1 VCM come here. And likewise, the same thing comes here, right? So here also you have GM, assume that GM1, GM2 are same. So GM1 VCM. Now these two currents are GM1 VCM, GM1 VCM. Net current, if you see KCL, net current going into the load will be zero, because up and down currents, the small signal current are both GM VCM, GM VCM. Therefore, we can say there will be no signal increase, there will be no signal coming to the output. That is, from the point of view of approximate small signal analysis, we can understand that why here the common mode, gain is poor. So here, of course, as is approximate analysis, we have not taken into account RO, etc., of the upper MOSFETs while considering current routing. So there will be, some RO associated here. There will be some current loss because of that, but we are ignoring all of that. But and conceptually trying to understand that why this is common mode is better. But if you look at this carefully, if we talk about the other previous circuits with fully differential output, how did we define the common mode gain? Common mode gain was defined as from this output VCM. What is the common signal coming here? V out CM. So let me call it V out CM. So for a V in CM, when you're applying a common mode input, what is the V out CM? So the output was taken single-endedly. So we are assuming, we are just looking at if you're increasing the V in CM, both are going down small little bit. When you're reducing, both are going up little bit. But in that case, we are basically not looking at the difference. We are just looking at both of them together. In this case, if you take the signal differentially, that common mode signal anyway gets cancelled out. For a fully differential amplifier, if you take the signal fully differentially, the common mode signals anyway cancels out fully, provided the circuits are exactly matched. Of course, if you have mismatches, we have seen that it will lead to common mode to differential conversion, and that will lead to corruption of signal. But if the transistors are fully, even if you have a common mode gain, you get it cancelled if you are taking the outputs differentially. But in this case, we don't have that thing happening. It is actually the signal is taken single-endedly. Therefore, this is actually, as compared to fully differential output, this is actually in real sense it is worse, because fully differential you were able to cancel out if you're taking signal differentially. In this case, you are forced to take it is only single-ended output, and therefore this is actually, if you look at the signal behavior, this is actually a finite, I would say, common mode gain that you are getting as compared to fully differential case. So that also we should keep in mind. So here, still it is important to look at the common mode gain in this case to make sure that, okay, in case you are taking single-ended output, you should know what is the worst case scenario, what is the common mode gain you can have. And also, in case you have mismatches, it will reflect, it will basically convert the single ended signal or basically common mode signal into differential. But in this case, actually, you are having possibility of transmitting the common mode signal from these two inputs to the output. That difference of the common mode analysis we should take care of. Is that clear? This part is clear. Common mode part is clear. Any question? Frequency response is very similar. Whatever we have done. So here, what is the dominant pole? Yes, what is the dominant pole? Quickly.
So I think still the output only, because again we have.
Yes, so this is AC ground. So AC ground anyway goes, and then you have first path. First path, as we said, it is from here to here. Second path is directly from here to here. First path, we have first pole here, which is again low impedance node. Therefore, it is not going to matter. And second at this node, which is the high impedance node, which is going to matter. For second path, that is the only pole. So in this case, you have a first path giving you gain like 1 plus s upon p1 into a2 upon 1 plus s upon p2, where p2 is just the dominant pole. Second path is giving you gain of a1 dash 1 plus s upon p2, where p2 is the output pole. Of course, if you have input side pole, that will also come into picture. So assuming that both inputs are identical, that will also add another pole term, provided you have a non-zero impedance driving these nodes, that will also come. So that we need to include. Then just one more factor will get added, and then you take the summation and find out. So ultimately, if you assume that the dominant pole is this one, it will give you one pole system, and other poles will be at higher frequency. Is that clear? This, in fact, will be the simplest OTA that you can have, operational transconductance amplifier, because it is also doing similar job. You are having input differential, single-ended output. But the gain will be limited. Here, you don't have very high gain unless you reduce the bias current too much and make the GMRO high. We know that GMRO scales up with root ID, right? So if your root ID, if ID is increased, the gain basically, sorry, if the ID is reduced, the gain goes up. So 1 upon root ID dependence. So if you want to do that, then you have to, if you want to get a very large gain, you have to reduce the ID. But then bandwidth will be sacrificed. So this stage is a simplest possible OTA. This can also be used as a feedback configuration. We can also use this as a voltage follower. Many cases when we don't need good gain, when suppose we have to do we have to design a very uh, simple voltage follower where the accuracy does not matter too much, very approximate voltage follower. So this circuit is good enough. We can make a approximate voltage follower using this circuit also, just connecting the negative input to the output. So simplest possible voltage follower, differential voltage follower. This is your positive input, negative input, you sort this. This is your voltage follower. So again, in this voltage follower, you need to make sure that whatever is the voltage, range, whatever you're applying over here and the following voltage over here, so the range will be determined by saturation region condition for the transistors. So if you apply, so in this case, there will be only a certain values or certain range of input voltage for which it will be reliably acting like a voltage follower. And since the open loop gain is relatively lower, you are having only one stage, so it will be less accurate. So you may have significant error between the input and output voltage. And if your gain is higher, then it will become closer and closer. So this is clear. So we have done the small signal analysis. We have done the frequency response, the single-ended as well as the common mode. Common mode frequency response remains same. Similar thing. So you will have that common mode rejection ratio reducing at higher frequency that is there in all differential amplifiers. So those things should be clear. Any question before we proceed further? This one I would like to cover maybe another small thing, which is if this is clear. Another thing is input swing or input common mode range. So in this case, how do we find out the input common mode range? Input common mode range means you are basically tying. We have discussed this with respect to fully differential amplifier. Here the condition is different. Why it is different? Because the two sides are not symmetric. One side you have a direct connected load, on the other side you have kind of current source load. So now here, which side will determine the upper limit of VCM? Lower limit remains again determined by the current source, W by L of this one and this one. Lower limit we know is we reduce the VCM, the tail current transistor will enter into triode region. Therefore, we should have VCM min determined by W by L of these two M1, M2 and the M5. What about upper side, VCM max? So lower side it is same as differential amplifier with resistive load. Upper side, quickly, upper side, what is the maximum value? How will you find?
So the upper MOSFET, the diode connected, has to be in saturation. So, and then VCM is gate to source. VD will be VCM VD VD minimum should be VCM minus V threshold, and then from the upper side we have VG3.
Yeah, VG3, you call it 3, 4. So you see, if I assume that gain at this node is very small, right? So from here to here, the diode connected load. So actual gain is coming here. If you simulate this circuit, apply a differential signal, the gain at this node will be much smaller than the output node. So you assume that this signal is in a fully differential amplifier. What happens? Both the signals are exactly similar and opposite, right? So peak to peak magnitude, you have a resistive low differential amplifier. Here you will get exactly same peak to peak amplitude in opposite direction differential. But this is an asymmetric load. So here, as we have seen, it is a diode connected load. We have analyzed the two paths separately also. So here the gain is small, where final gain is coming here much larger. So we can assume that this DC is almost same. It is not, even if you are applying some input signal, this is remaining close to the DC value. So therefore, whatever is the VG3 required to support ID by 2, as compared to that VG3, maximum VCM will be VG3 plus VT of 1. Because if it goes higher than that, then M1 will be entering into triode region. M3 is anyway always in saturation. If you increase the gate voltage of M1 too much, eventually it will go higher than VG3 plus VT1, and then M1 will enter into triode. Is that clear? Upper, if you look at this side, what would have been the case here also? Again, VG3 is constant, but this drain voltage is not equal to the gate voltage. So if we had to look at only the second side, what would have given you? Suppose you have the current source load. You have basically the current source load where you don't have this VG3 only. So we have discussed this earlier. So what will be the output? VCM max in this case? That is not deterministic, right? That is first of all, in this case, it depends upon what is the output DC voltage, right? So in order to look at the output DC voltage, what is the maximum output DC voltage you can bias it for? VG3 plus mod VTP, right? So this maximum output DC voltage is basically VG3 plus mod VTP. And then if I assume this gate voltage can go higher than that by mod VTP, that will determine the upper level. Generally, of course, will not keep this this to the maximum value. Otherwise, upper side you don't have any swing. For maximum symmetric swing, you will probably place it somewhere. So in a fully differential case, the way you calculate the VCM max and min will be determined by what is the output DC level you have set. And in order to get the maximum symmetric swing condition, you know how to set that output. V out min possible by 2. V out max possible will be what? VG3 plus mod VTP, and V out min will be VG, the lower side VG2 plus basically minus mod VT minus VT2. So this by 2 will give you the DC bias point, appropriate DC bias point. Now, with respect to that DC bias point, we will have to see what is the maximum basically allowed DC level. In this case, however, you have a diode connected load, and we are looking at the diode connected side because here the DC potential at the drain for the common mode is determined by this diode connection. That's what we have in the common mode analysis. Also, we have assumed the same thing, that as long as the input is common mode, both the outputs are going to be same, DC potential are going to be same, and therefore you're going to get the two node voltages following each other. And therefore, from here you can find out what is the input common mode range. Is that clear? This point should be clear. Output swing in this circuit, output swing, what will determine the output swing? What we saw is this node is going to have very small swing, whereas output node is actually having much larger swing. For the output swing, we will not consider the diode connected side. We will only consider the output side. because here anyway we are not considered about the swing on the diode connected side. It is anyway low. So we will only look at the output node which is constituted of M4 and M2. So what is the swing consideration for a given VG3? V out max will be VG3 plus mod VTP, and V out min possible is what? V out min possible is whatever is the DC potential at this node, VG2 minus VT 2, right? But is it is that the thing we are going to look at? What we need to see is with respect to the DC bias point. This is of course the maximum minimum achievable value. That is true. But what if I ask you to find out the maximum symmetric swing? What will you do?
So VG2 in turn depends on the M5.
Need to look at. So this is the V out max and V out min. So without troubling any transistor and making them enter into triode region or go out of saturation region, this is the maximum and minimum signal levels or voltage levels that you can achieve at the output, which is the drain of M4 and M2. But if I say what is the symmetric swing maximum, how will you find? Quickly. Fast, tell me. Very easy. We have already discussed
So
this kind of thing earlier.
we should find the like midpoint of V out max and V out min, and then whatever is the difference between that point and V out max should
What
be
do
the
you mean?
maximum.
Then is simply by 2. If we are
Yeah.
just looking at midpoint, then this maximum symmetric swing will be just this by 2. Then why will I ask this question? This concept we have discussed while discussing diode connected load. If you simply say that it is maximum symmetric swing is V out max plus V out min by 2, then there is no point. It is trivial. For that, you need to find out what is the actual DC potential. Right now, the actual DC potential is determined by what? It is determined by VG3, because under DC condition, V out DC is equal to VG3, right? That's what we have discussed. DC condition, common mode input, output voltage will be equal to the other side drain voltage, which is equal to VG3, right? Now, can you tell me?
So then, like, so then,
So V out max minus VG3 will give you the upper side, how much margin you have, and VG3 minus this quantity will give you the lower side margin. Whichever is
minimum.
lower, that will be your max symmetric swing. Is that clear?
And the swing will be about VG3, right?
Yeah. So ultimately, the bias point here is VG3. This is in absence of input. This is VG3. If your both the inputs are exactly the same DC without any AC signal, this is at VG3. So from VG3, how much higher side, how much it can go? It can go maximum to VG3 plus VTP. Lower side, how much it can go? To this much. So whatever is the smaller difference, V out max minus VG3 or VG3 minus V out min, whichever is smaller, that gives you the max symmetric swing ideally. Is that clear?
Yes, sir.
So then to get maximum swing, we should try and match VG3 and VG2, right?
No,
Then,
means how will it? So that is not. So for maximum swing, you will try to basically get midpoint of these two equal to VG3. So for that you will get the value.
yes. Okay.
Yeah. So I hope we have already 7:15. So let us stop here. Any question? Let us. I will think about the proper assignment on this, at least so that you can do this. And whatever differential amplifier we have discussed today, based on that also some op-amp configuration we will study. And in feedback, how do you analyze the loop and how do you also look at the phase margin, etc. We'll look at that for this particular topology. And then there will be some other interesting things related to compensation, stability. Following that, we will also look at fully differential amplifier, where the first stage, second stage are both fully differential. In yesterday's class, we discussed OPAMP or OTA, where the first stage is fully differential, second stage is single-ended. In this case, if I go for a OPAMP based on this topology, what will I do? I need to connect the common source stage again to the output. Here you have only one output, because in this case, the differential amplifier itself is not fully differential. It is differential input, single-ended output. So only output available is this point. So I need to connect a common source to this one. So how will I connect? What kind of common source will I connect for this particular configuration?
So we said like differential input and single output. We already have this, right, for current mirror load.
So what is the purpose of putting the second stage?
Low output impedance.
Low output impedance.
Like
In the last example, we had low output impedance in the second stage.
No, we don't. But for an op-amp, we want that, so we have to add the second stage.
No, for the time being, what is the purpose of in the previous stage? What was the purpose of putting a second stage? So that is getting a higher gain. So in order to get a higher gain, the low impedance will come, but first of all, you need to have an overall large gain. Here, the gain is still GMRO by 2. Whereas in the previous amplifier that we have discussed, it was GMRO whole square, right? GMRO whole square by 2. So as compared to that, this is still much lower. So I need to still go ahead and increase the gain. So if I put another common source stage, that will give me another GMRO. So that will become equivalent to the previous topology that we have discussed, at least in terms of gain. So what my question is, what common source are we going to put?
Current source load, I think. Then we'll get a GMRO.
And is it going to be a PMOS current source? Is it going to be a PMOS input or NMOS input?
DC level is VG3, which is low. NMOS input, I think so.
Oh, why NMOS input?
Like V out DC level, we had said is VG3 and VG3.
What is DC level VG3? It is a gate voltage of a PMOS. Why will I apply a gate voltage of a PMOS to the gate of NMOS?
Oh, okay, sorry. Yeah.
So you will just have another PMOS, and then you will have this current source. This is a two-stage op-amp, which is one of the most common, and we will analyze this maybe in detail tomorrow. So this is clear. Any question on this? And then after this is completed, we will look at the fully differential topology. That is also important. And after that, the op-amp discussion will come to a close, and we will look into some other. So gradually we will go towards more advanced topics. And for this also, for op-amp and differential amplifier, I have given you yesterday a very small assignment. I will post another assignment for today's discussion. So please spend time on simulation. If you want to take up projects, you have to be. This is the peak period in summer. If you don't spend time on building basics, on doing simulations, and improving your understanding, probably you will not get this kind of time again ever. That you should understand. Next summer will be internship. After that, you will be having admits and this and that. It will be difficult. So this is golden period. If you want to get into this topic, you should invest time passionately to cover the theory part, also do the simulation as much as possible, understand what is happening in the circuit, look at it from different angles. So whatever analysis I'm giving you, it is bare minimum. I don't want to, but that is a very small exercise I gave you, but actually I should give you much more, so that you are able to absorb things and you are able to do many more things on daily basis. Then only you will be able to cope up with any good projects in this area. Otherwise, it will just remain like a formal course. So I may give you more time taking assignments. If you are really committed, if you are going ahead with the ambition that you want to do good projects on this very soon, please try to complete those assignments. That will be very helpful, right? So don't, if you think that, okay, just 1 hour, 1.5 hour, 2 hour I will give and that is good enough, probably not very correct. So if you are really in the summer, if you, whatever I'm teaching, if you are able to catch up, if you are able to do simulations based on that, you will have solid background on the basis of which, even before summer, right now May, we have already reached mid of May. By end of May, or early first week of June, you will have enough things covered, so that you can get started on some nice projects. So that is the idea. So please be ready for some ramp up in the assignment. I may start giving you more assignment than usual. Spend more time. Get that. I always try to include some challenges in the assignment, so that you have to apply some brain, do some analysis, try to see, try to address those problems, so that you can appreciate what is going on. And just like at the end of common source, at the end of single stage amplifier discussion, I gave you one relatively time taking assignment, which we discuss in detail in the class. Likewise here also, whatever assignment is given, we will discuss one by one in the class. Okay, so let us conclude today, and we will meet tomorrow. Any question before we conclude? Any question before we conclude? Okay, so let us exit. Thank you.